Hey, welcome back everybody. Today we are going to discuss continuity. This is one of the really big theorems of mathematics, of calculus, and you will definitely see this on the AP exam. First and foremost, continuity is what we call an existence theorem. So it's something we are going to have to prove every time. So imagine we have a function at some x value c, some f of x. What we want to find out is if we're at this function, at the point C, would this function be considered continuous? And of course, from our previous discussions in class, we know that it is. One, I can draw it without ever lifting up my pencil. So how can we prove this mathematically? To do that, we have a set of rules for us. So here we go. Step one, we have to show that the value of the function actually exists, that we can have a value there. In other words, we have to find f of c. Next, we have to look at the limit of the graph. We have to see that the limit exists. And to do that, we have to do our process. We have to make sure that the limit as we approach c from the left equals, now notice how I write this, equals the limit as x approaches c from the right of our function. And there's a reason we're going to do this. We'll talk about this in a couple of days, why we like to write it this way. And then the third one, we have to make sure that the limit of our function actually equals the value of our function. And if we can prove all three of those, we would say, therefore, f of x is continuous at x equals c. So let's take a look at a bunch of examples here. And this is really so here we go. Let's look at the function, the line, y equals x plus 1. We want to know, is this going to be continuous at x equals 3? Now, this is a big fat duh. Lines are continuous. So to solve this, but to prove it, it's not just saying, duh, it's going to work, dude. We have to physically show it. And to do that, the first thing we're going to do is we're going to find the value. Step 1, find the value at f of 3. And if we did that, we would get 3 plus 1, which is 4. Step 2, we're now going to look at the limit as x approaches 3. And that I can do really easy. I'm just going to plug it into the same one. 3 plus 1 is 4. Duh. Now, if you notice, these are equal. And that's what we want. It looks like a sad face. Aww. It's doing calculus. All right, so we want to make sure that these are equal, and once they are equal, then we can write our answer. And we're going to write it this way. Therefore, f of x, watch how I note this, is continuous at x equals 3, and we're going to say because the limit as x approaches 3 of our function is equal to the value of the function at 3. Now, there's a couple ways you can write this, but the AP, in this case, really likes a sentence in this case. And that's how you're going to write it. Once you get the value and the limit, and they're the same, and they're equal to each other, you just write your statement. So number 2, let's try number 2. Now, number 2, I can factor this. I'm not saying the limit doesn't exist, and we can do that x plus 1, x minus 1 over x plus 1. These will cancel. So I know that the limit will exist. But we're not looking for the limit here. We're just trying to see if this is continuous. So the first thing I'm going to do is I'm going to check for the value. I want to find f of negative 1. And if I plug it in, I get 1 minus 1 over negative 1 plus 1. And we talked about this earlier. The top here is just 0, and the bottom is 0. Now be careful. This is not indeterminate. Indeterminate deals with the limits. This is really saying that the value does not exist. That's what that says, that the value, Denis, does not exist. So in this case, the function's not going to be continuous because it doesn't have a value. Now, we're not saying it doesn't have a limit. We're just saying it doesn't have a value. Matter of fact, we talked about this earlier. We have a hole there, dear Liza, a hole. So we would say in this case, f of x is not continuous. Spell out the word continuous. At x equals negative 1, or c, because, and we're going to say it this way, the limit as x approaches -1 of our function f of x does not exist. And that's it. There's our answer. Remember, write it as a sentence. The AP is really in the sentences this year. This is a lot of writing, but this is an easy 4 points on the AP test. All right, question 3. Let's try this one. We want to know if this composite function is continuous at x equals 3. So I'm going to test it. Step 1, find the value at 3. Now I've got to be careful which one of these represents the value. This one. It has the equal sign. So I'm going to plug my 3 into the bottom one. 2 times 3 plus 4, and that becomes, what's that, 10? Very good. Nice job. Now we have to test the limit. Now unfortunately for this one, it's not as easy as just plugging in. For number 3 here, we have to test both sides. And when we have to test both sides, it's nice to write it this way, because you're checking to see if they are equal to each other. So this is kind of the way I kind of prefer it. AP will accept it other ways. So for this one, we're going to get the limit as x approaches 3 from the left. And from the left, we're on this top one. There's my left, because it's less than. And I'm going to use this x squared plus 1 equal to, now the limit as x approaches 3 from the right. Well, on the right, we're on the bottom. That's going to be this 2x plus 4. And now just plug in. I plug in here, 3 plugs in here. I get easy. 9 plus 1 is 10. 6 plus 4 is 10. So yes. And now we're going to say this. Therefore, the limit as x approaches 3, not from left to right, just 3, of our function is 10. So take a look. The value was 10, and our limit turned out to be 10. Would this be considered continuous? And of course the answer is yes. So we're going to say, therefore, f of x is continuous at x equals 3. And that is because the limit as x approaches 3 of our function equals the value at 3. A lot of 3's here right there. So and there is our statement. Very easy to do. It is a little bit of writing, but you're not going to have too much to do tonight, unlike BC. Feel sorry for those poor chaps. They got a lot more writing. All right, now this one right here, we want to see if we're continuous at c equals 2, or x equals 2. So don't panic. So the only ones that have a 2 are the first two. So I really don't need the bottom one, because that's only dealing with 4 and 6. We'll talk about something like this later on this week. So I want to find out if this is continuous at 2, same thing. I want to find the value at 2. At 2, which one is the value? Out this bottom one. There's my equal sign. So it's going to be 2 natural log of 2. Step 2. Now I want to find the limit at 2. Well, this is a little bit trickier. So I need a limit as x approaches 2 from the left. And I want that to be equal to the limit as x approaches 2 from the right of our function. Well, on the left, which one are we on? That's right. We're going to be on the natural log, because this here says less than 2. So that's going to be natural log of x. For greater than or equal to, for plus 2, that's going to be here. This is actually saying x is greater than 2. So that's going to be on the right side, and that is x natural log of 2. And this is kind of cool. Look at here. If I plug in, I get natural log of 2, and over here I get 2 natural log of 2. Now, clearly these are not the same. So even though the value exists, the limit exists, but the value exists, but the limit here does not exist. So we're going to say that here that this is not continuous, because it does not have a limit. F of x is not continuous, spell out that word, at x equals 2, because the limit as we approach 2 does not exist. Write out your sentence every time. All right, so we've been talking about continuity and how we can prove a function is continuous. It's just a very simple 3-step process. 1, check for the value. 2, check for the limit. 3, see if they're equal to each other. Now we're going to talk about, well, if a function's discontinuous, how can we describe that discontinuity? That's what we call it, discontinuity. And you might have talked about this last year in pre-cal. If a function is not continuous, then we say there exists what's called a discontinuity. And there are three main types. And there are other ones, but these are the three main ones. The first one is a point discontinuity. A point discontinuity talks about a hole. We used to call them a hole. So it could look something like this, or it could just be that that point was literally just removed. As a matter of fact, point discontinuity is what we call removable. It's the only one that we actually consider a removable discontinuity. The next one is an example would be something like x minus 4 over x squared minus 16. If I factor the bottom, I can cancel the x minus 4's. We remove the continuity, the part that makes it continuous. The next one is a jump. These are the Mac Daddy of them all. A jump would look like this. This is your basic step function. This would be like your weird absolute value function, your greatest integer function, and things like that. We're moving along and we jump to the next part. The next one would be asymptotic. Sometimes you'll hear people call these infinite discontinuities. I'm old school, it's asymptotic. I just like to say the word, it's asymptotic. Okay, it's not cool for me. And these are like your 1 over x's, your 1 over x squared. These are easy. We recognize these from middle school. They look like that. Now, the only one that you want to really worry about in terms of removability is point. The other ones, no other type, are what we consider discontinuous. Removable. So that's our notes for today. Take a look at the homework. Take a look at these again if you need to. I'll see you later. Bye-bye.